Alright, let's go. Number 10. The Horizon Problem. Astronomers in the late 1970s were doing something almost boring, mapping the temperature of the cosmic microwave background, the leftover heat of the early universe across different patches of sky. They expected small variations, sure, but nothing that would break physics. Standard cosmology says regions of space that have never been in causal contact, never close enough for light or any signal to pass between them, should have no reason to match. No shared history means no shared temperature. What they found instead was a universe that agreed with itself almost perfectly. Patches of sky on opposite sides of the observable universe, separated by distances that light itself has not had time to cross since the Big Bang, sit at 2.725 Kelvin, differing by only about 1 part in 100,000. Robert Dicke and Jim Peebles at Princeton formalized the problem in the late 1970s. How do regions with no possible communication end up thermally identical? Proposed fix number 1. Maybe it's a coincidence of initial conditions. Rejected. The odds are absurd. Proposed fix number 2. Maybe the speed of light was different early on. No consistent model survived scrutiny. The only explanation physicists settled on was Alan Guth's 1981 Inflationary Universe paper in Physical Review D, which proposed that everything we see was once small enough to touch, then expanded faster than light itself could have separated it. It's an elegant patch. It is also, as you're about to see, a patch resting on something we've never directly observed. Every direction you look tonight, the sky is whispering the same temperature, a memory of contact that, by the rules of relativity, should never have happened. That fix, though, comes with its own bill to pay. Number 9. The missing inflaton. Alan Guth wasn't trying to invent the most influential idea in modern cosmology. He was a particle physicist at Cornell in 1979, working on the magnetic monopole problem, why we don't see these predicted particles anywhere in the universe. Standard particle physics said the early universe should be dense with monopolies. Observation says there are effectively 0. Guth's solution required a period of exponential expansion, and that expansion needed something to drive it, a hypothetical quantum field named the inflaton. The setup was supposed to be temporary, solve the monopole problem, explain flatness and the horizon problem as side benefits, then hand the universe back to normal physics. The stumble was that the inflaton, despite driving what may be the single most consequential event in cosmic history, has never been detected, isolated, or confirmed to exist as an actual particle or field. Guth's 1981 paper, and the improved versions from Andre Linde in 1982 and Andreas Albrecht and Paul Steinhardt the same year. All require this field, but none of them can tell you what it's made of. Proposed candidates include the Higgs field, various grand unified theory fields, and dozens of custom-built scalar fields invented purely to make the math work. Every candidate has been either ruled out or remains untestable with current instruments. The implication is uncomfortable. The leading explanation for why the universe looks the way it does depends on a particle we have never once measured. Your existence, and the existence of every galaxy above your head tonight, rests on a field that so far might as well be a placeholder. If the driver of inflation is invisible, what about the shape it left behind? Number 8. The Flatness Problem. Again, cosmologists in the 1970s were simply trying to measure the overall geometry of space, using early data on the universe's density compared to a theoretical critical value. Standard Big Bang cosmology without inflation predicts that any tiny deviation from perfect flatness in the early universe should have been dramatically amplified over billions of years. The same way a pencil balanced on its tip falls further from vertical the longer it stands. Given the universe's age, the density should have drifted wildly from flat by now, in one direction or the other. Instead, the Planck Satellite Collaboration's 2018 cosmological parameter results measured the curvature density parameter, omega k, at essentially 0, constrained to within 0.5%. That means at 1 second after the Big Bang, the universe's density had to match the critical value to within 1 part in 10 to the 16th power. Robert Dicke first framed this as a fine-tuning catastrophe in 1979. Proposed explanation 1. Maybe flatness is just how the universe started. No reason needed. rejected by most cosmologists as an unsatisfying non-answer that abandons explanation altogether. Proposed explanation 2, anthropic selection, we only exist to measure a flat universe because a non-flat one couldn't support galaxies. Still debated, still unproven. Inflation remains the dominant fix, stretching any initial curvature flat the way stretching a balloon flattens its surface locally. But inflation-solving flatness only works if inflation itself actually happened the way the math requires. You are standing, right now, inside a geometric coincidence so precise that a single misplaced digit that far out would have meant no stars, no planets, no you. And if the shape was engineered by inflation, the next question is who flipped the switch? Number 7. What started it? Or stopped it? Physicists building inflationary models weren't trying to explain cosmic origins from nothing. They were trying to patch 3 separate problems: horizon, flatness, and monopolies, with a single mechanism treating inflation as a mathematical tool first and a physical event second. The standard assumption was that once you accept a scalar field capable of driving exponential expansion, the field would naturally roll down an energy potential, start inflation, and then end it cleanly when the field settled into a lower energy state, converting its energy into the hot particle soup of the traditional Big Bang. The stumble is that no version of inflationary theory has a confirmed answer for what set the initial conditions that triggered this field to begin rolling in the first place, or precisely what shape its energy potential takes to guarantee inflation ends smoothly rather than not at all. Andre Lin's 1982 New Inflationary Universe paper in Physics Letters B required extremely fine-tuned potential shapes to avoid what's called the graceful exit problem, where inflation, once started, doesn't stop the way it needs to. Proposed Fix 1, chaotic inflation, Lind again in 1983, lets inflation start from nearly any initial condition, but at the cost of requiring an enormous, still unobserved energy scale. Proposed Fix 2, hybrid inflation models, add extra fields to control the ending, but multiply the number of unconfirmed particles required. Every patch fixes the exit while deepening the mystery of the start. Somewhere in the earliest fraction of a second, something switched on a process capable of creating everything you have ever loved. And no equation currently tells us why that moment, and not some other moment, or no moment at all. Some physicists looked at that switch and found it might never fully turn off. Number 6. Eternal inflation's strange prediction. Andrei Linde and Alexei Starobinsky, working through the mid-1980s on the technical mechanics of how inflationary fields behave under quantum fluctuations. We're simply trying to model the field's behavior more rigorously, checking whether inflation would end uniformly across all of space at once. Standard expectation held that inflation is a single event, it starts, it stretches space, it ends everywhere roughly together, and the hot Big Bang begins. Quantum fluctuations shouldn't change that basic picture. The stumble came when Linde's 1986 paper in Physics Letters B showed that quantum fluctuations in the inflaton field means some regions of space will always, by pure probability, inflate slightly longer than others. Those regions expand faster, become larger, and within them, new subregions form where the same thing happens again. The numbers are almost absurd to say out loud. Inflation, once it starts anywhere, may never stop everywhere, generating what Linde termed a self-reproducing, eternally inflating fractal structure of universes, each one potentially with its own physical constants. Proposed explanation for avoiding this: modify the potential to force uniform ending. Every attempt so far still permits eternal inflation in some region of parameter space. Proposed rejection: dismiss it as an unphysical mathematical artifact. Many cosmologists, including Linde himself, argue it's a genuine prediction of the theory, not a flaw. If eternal inflation is real, our entire observable universe, everything you will ever see or touch or measure, is one finite bubble in a process that never finishes, happening right now, forever, somewhere you can never reach. But step back from the multiverse for a second, because even the single bang you were taught in school isn't what it sounds like. Number 5. The Big Bang isn't actually an explosion. Georges Lemaitre, the Belgian priest and physicist who first proposed an expanding universe model in 1927, was working through Einstein's general relativity equations, trying to understand why the universe's redshift data, later confirmed observationally by Edwin Hubble in 1929, showed galaxies receding from us in every direction. Popular imagination assumed an explosion. Matter blasted outward from a central point into pre-existing empty space, the way a bomb detonates in a room. Standard relativistic cosmology says nothing of the sort. The stumble, for anyone approaching this expecting a fireball with a location, is that the Big Bang describes space itself expanding, stretching the distance between all points simultaneously, with no center and no exterior into which anything is moving. Lemaitre's own equations and Alexander Friedmann's earlier 1922 solutions to Einstein's field equations published in Zeitschrift für Physik describe a uniformly expanding metric, not a projectile in motion. Every galaxy is not flying away from a central blast site. Every galaxy is standing still locally while the space between all galaxies stretches, the same way dots on an inflating balloon's surface move apart with no dot at the center. Proposed lay explanation, the explosion metaphor, persists in textbooks and documentaries because it's intuitive, and it is flatly wrong, misleading generations of students about the geometry involved. There is no place in the sky where the Big Bang happened, because it happened everywhere, including exactly where you are sitting right now, which was, at that moment, the entire universe. If there's no center to point to, there's also a wall we can't see past. Number 4. We can't see before recombination. George Smoot's team on NASA's Cosmic Background Explorer satellite in the early 1990s was attempting something methodical, precisely mapping the temperature of the relic radiation predicted by Big Bang theory, first detected accidentally by Arno Penzias and Robert Wilson in 1965. The standard model predicted that this radiation, the cosmic microwave background, should be the earliest light in existence, released roughly 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, a moment called recombination, finally letting photons travel freely instead of scattering constantly off free electrons. Before that moment, the universe was an opaque plasma. No light could travel any meaningful distance without being absorbed and re-emitted. The stumble isn't a violation of physics, it's a hard wall. Smoot's code results, published in the Astrophysical Journal Letters in 1992, confirmed the CMB's near-perfect blackbody spectrum and its tiny anisotropies, but by definition, this is the earliest direct light-based observation possible. Everything before recombination, the entire inflationary epoch, the moment the inflaton field decayed, the earliest fractions of a second, is invisible to any telescope that has ever existed or ever will, because no photon from that era could escape. Proposed workaround 1, gravitational wave detectors, could theoretically catch ripples from before recombination. None have yet been confirmed at the relevant frequencies. Proposed workaround 2, neutrino background detection, remains technologically out of reach. Every claim about the first 380,000 years, and especially the first second, is inference built on models, never direct sight. You were separated from the true beginning of everything by a wall of light that cannot be seen through. Only reasoned around. Yet somehow, out of that unseen chaos, everything you can see was written into existence. Number 3. Quantum fluctuations became galaxies. Vyacheslav Mukhanov and Gennady Chibisov at the Lebedev Physical Institute in Moscow, working in 1981, were exploring the theoretical consequences of applying quantum field theory to Guth's newly proposed inflationary model, mostly as an exercise in mathematical consistency. Standard classical physics offered no mechanism for why matter in the early universe wasn't perfectly smooth. A perfectly uniform universe should have stayed uniform, with no seeds for stars, galaxies, or you to eventually form around. The stumble was realizing that the Heisenberg uncertainty principle guarantees tiny, unavoidable quantum fluctuations in any field, including the inflaton. And that inflation's exponential expansion would stretch those microscopic quantum ripples up to astronomical scale before they had any chance to average out. Mukhanov and Chibisov's 1981 paper in JEP letters, later expanded by Stephen Hawking and independently by Guth and So-Young Pai in 1982, showed these stretched fluctuations become the density variations later imprinted on the CMB and observed precisely by the Planck satellite's 2018 power spectrum measurements. The numbers involved are almost impossibly small. Fluctuations on the order of 1 part in 100,000 were enough, over billions of years of gravitational amplification, to collapse into every galaxy, star, and planet that exists. Proposed alternative explanations, including cosmic strings and other topological defects, were tested against CMB data and statistically excluded. The consequence is unsettling to sit with. The arrangement of galaxies across the observable universe, and therefore the specific location of the star you orbit, was decided by literal quantum randomness in the first fraction of a second, meaning the universe you live in is only one of countless statistically possible outcomes that could have unfolded instead. Trace that randomness all the way back, though, and you hit something physics simply refuses to touch. Number 2. The singularity isn't really explained. Stephen Hawking and Roger Penrose, working through the late 1960s, were extending Penrose's earlier work on gravitational collapse inside black holes, originally trying to prove that collapsing stars must form a genuine singularity rather than some exotic stable state, applying the same mathematics to the entire universe running in reverse. Standard general relativity predicts that if you trace cosmic expansion backward far enough, all matter and energy converge to a point of infinite density and zero volume, a singularity where the equations of physics themselves stop producing meaningful answers. The stumble is that this isn't a limitation of our instruments, it's a mathematical breakdown. Hawking and Penrose's joint 1970 paper in the Proceedings of the Royal Society, The Singularities of Gravitational Collapse in Cosmology, proved under fairly general conditions that general relativity alone guarantees this breakdown, given a universe that is expanding and contains ordinary matter. Proposed Resolution 1. The Hartle-Hawking no-boundary proposal from their 1983 paper in Physical Review D uses imaginary time to smooth the singularity into a rounded, boundary-free beginning, but remains mathematically speculative and experimentally untested. Proposed Resolution 2. Loop quantum cosmology's big bounce models replace the singularity with a prior contracting universe, equally unconfirmed. Proposed Resolution 3, Roger Penrose's own later conformal cyclic cosmology, treats the Big Bang as the rebirth of a prior universe's infinite future, controversial, and disputed by most of the cosmology community. General relativity, our most successful gravitational theory, mathematically insists the universe began at a point it cannot describe. The very first moment of everything is not a mystery physics is close to solving. It's a wall physics itself built. Which brings us to the entry that isn't really a discovery at all. It's a confession. Number 1. The honest answer. Cosmologists across the past 4 decades weren't trying to admit defeat. Alan Guth, Andre Linde, and Paul Steinhardt each spent careers refining inflationary theory into what is now taught as the standard model of the early universe, supported by CMB measurements, large-scale structure surveys, and the Planck satellite's precision data. Standard science communication tells the public that the Big Bang is settled, textbook, done, a story with a beginning we understand. The stumble is that some of the theory's own architects disagree. Paul Steinhardt, one of inflation's co-founders in 1982, co-authored a 2013 paper with Anna Ijos and Avi Loeb, later expanded in a 2017 Scientific American piece titled Pop Goes the Universe, arguing that inflation, once you follow its logic fully through eternal inflation, doesn't actually predict a unique, testable universe at all, undermining the theory's scientific standing from the inside. The numbers are stark. Despite 50 years of refinement, cosmologists still cannot state with confidence what physically happened before, roughly 10 to the negative 36 seconds after the Big Bang, cannot confirm the inflaton exists, and cannot resolve the initial singularity mathematically. Proposed defenses of inflation point to its successful predictions for flatness and the CMB's fluctuation spectrum. Proposed criticisms point out that a flexible enough theory can be adjusted to predict almost anything, weakening its falsifiability. No resolution has satisfied both camps. The honest answer, the one rarely said out loud in documentaries, is that our most successful scientific framework for the origin of everything cannot yet tell you why there was a beginning at all, or what, if anything, came before the question made sense to ask. 10 entries. One thread running under all of them. The universe is not confused. We are. Every anomaly on this list doesn't live at some distant, forgivable edge of human knowledge. The horizon problem. The missing inflaton, the singularity we can't model, these sit at the exact center of our most tested, most celebrated theories. We built cosmology's cathedral, and then found we couldn't explain its foundation. Somewhere behind a wall of light we will never see past, something happened that made you, your galaxy, and every star above you possible. And physics can describe almost everything about it, except the one thing you'd actually want to know. Why? If you want to see more videos like this, click the video on screen now.